Okay, let's get started, everyone. So today we are going to have a class on the iPad. So I would recommend following along on pencil and paper or whatever, your own tablet. I will also post these notes after class, so you will be able to study from them after the class is over. All right, so before we get started, just some notes. First, you have a quiz, which I forgot to mention in the last class. This quiz is due on Monday on Gradescope. It's just 2 questions, not graded for correctness, but we do expect that you at least attempt to answer each question. The purpose of these quizzes is generally to give you some idea of the concepts that you'll need to know for the exam, and also give you an idea of some of the reasoning that you will be expected to perform on problems in the exam. It's also essentially a participation check just to make sure you are following along with the topics of the week. All right, so other things, your homework is due on Friday. Your group assignments, if you want to make those, is also due on Friday. Any other questions about class-related things? All right, let me check on YouTube. Okay, it's a little annoying to check on YouTube with this setup. So let us move on to today's topic, which is training neural language models. Okay, so is that readable from people back there? Okay. So remember last time we talked about the forward propagation phase of a neural language model. So how we get from a sequence of word embeddings to a distribution over the next word. Today, we're going to be talking about how we actually make a neural language model produce good predictions of the next word. And so if you remember from last time, we said that neural language models contain what are called parameters, right? And so some examples of these from our concatenation-based feed-forward layer were the weight matrices, W1, W2, the word embeddings, C3, blah, blah, blah. So these are the parts of the neural language model that are actually learned, right? We start with random parameters and we adjust them through the training process. So these parameters are randomly initialized. This means that their values, like all of those elements in the matrices and the initial word embeddings, are completely random at the start of training, just random numbers. And as a result, the probability of the next word that's computed by one of these language models is also random at the start, right? So if I gave a randomly initialized model the prefix students opened there, I should not expect this model to put high probability on books without any sort of adjustment to these random parameters, right? It has no idea that books is plausible given this prefix. Our whole goal is to adjust the parameters such that books becomes a high probability next word given this prefix. So conceptually, by training the neural language model, we adjust its parameters to maximize the likelihood of the training data. So remember, we talked about the maximum likelihood estimate in the context of n-gram models, right? There, we were just counting occurrences in the training data and dividing by other occurrences. And the whole goal was to maximize the probability of the training data. That's exactly what we're going to do here, except we have a different kind of model. We're not just counting and dividing. We are going to do something called gradient descent in order to update our model parameters to maximize the probability of, say, books given students open there. All right, so let's get back to our concatenation-based neural language model that we looked at in the previous class. We'll just use this for sake of demonstration. So I will draw it out here with our favorite example, students open there. Okay, so let's see here. We have students opened there. And so the first thing we do in any sort of neural language model is associate these tokens with their corresponding embeddings, right? So I have an embedding for students, an embedding for opened, and an embedding for there. These are the embeddings associated with those three words. We'll call those C1, C2, C3, following the notation from the previous class. So now I had a way to obtain this hidden state, right, which we will call H, that is a function of these three embeddings, right? And what is the way we did this? We talked last time about using an equation that looks something like this. So we take a nonlinearity and apply it to this matrix vector product. And here I'll use a different notation to denote the concatenation of these three embeddings with each other. So this here refers to the concatenation operation, the semicolons here. So basically, I take the three embeddings, I glue them together, I pass them through a linear layer and apply a nonlinearity like the ReLU that we discussed in the previous class. So that's how I get my hidden state. And then the final thing I want to do is obtain from this hidden state the probability distribution over the next word, right? So last time we discussed the softmax layer, right? That was the module that we passed this hidden state into to obtain a probability distribution. So we want something that is going over our vocabulary, let's say A to zoo, and books is over here, and so we have a low probability on all these other items here, and then a very high probability on books, right? This is what we ideally want out of this model. So let's call this O for the output distribution. And O here is softmax of W2H. So this matrix vector product, we use this to project H into the space of the vocabulary, and then we apply the softmax function to squash that result into a valid probability distribution. So this is just a recap of the forward propagation phase of the concatenation-based neural language model. So now, one question here is, what are the parameters of this model as I've just drawn them out here? Anyone have any ideas? So W1 and W2 are certainly parameters of the model. Right, and all of the Ci, so let's say C1, C2, C3. What about H? Is H a parameter of the model? Why isn't H a parameter of the model? Someone raise their hand and tell me. Yes. That's true. H is not a parameter, it's just a function of the actual parameters of the model, right? It's an intermediate variable. We are not going to be learning H, right? We are going to be learning the parameters, and then H will change as a result of adjustments to the parameters of this model, right? You can see if I change W1 in some way, H as a result will also be changed through this equation. All right. So let me just check on YouTube to see if there's any questions. Where can we find the quizzes and homework? They are on the website and posted on Piazza. If you're not on Piazza or Gradescope, please email the instructor's account and we will add you. All right, let's get back to this. So now, let's go through the high-level steps of how to train a network that looks like this. So, let's say steps to train an neural language model. Okay, so step one is pretty critical, and also we are going to use the same exact implementation of step one for all language models, all neural language models that we see in this class. So the first thing we need to do is define a loss function. So if you've taken a machine learning class, you have probably seen a variety of loss functions. We'll call this L as a function of theta. And just as a bit of notation, when I refer to all of the parameters of the model, I'm going to use the variable theta. So here, theta is just this set of all of the model's parameters. So it's a convenient way of referring to every single parameter in the network. And a model is just defined by the set of parameters that comprises that model, right? So when I say L of theta, that means that there is a loss function, and the function itself outputs a single number, a scalar, and that scalar is dependent on all of the parameters of the neural network. So what does our loss function do? Intuitively, it tells us how bad the model is at predicting the next word. So if I gave my model students open there and it put 100% of the probability on zoo, this would be a model that would obtain a very high loss, right? Compared to if I gave the model students open there and it put, like, say 60% on books, this model ideally would get a lower loss, right? So it's telling you how good or bad the model is. A higher loss indicates that the model is worse. So there are some constraints on what this loss function, what properties this loss function has. If you've taken a machine learning class, you've probably seen that it is ideal for optimization if the loss function is smooth and differentiable. Meaning we can take its derivative at every point. As we will see, this is a critical component of using the gradient descent algorithm. All right, so given these, this loss function, and we'll go into the specific loss function used in neural language models a bit later, but I just want to get through the high-level steps first so you have a conceptual understanding of how to train one of these things. So given the loss function, we're next going to compute the gradient. I'm just going to highlight this because it's very important, of L with respect to theta. So what does the gradient tell us regarding this loss function? The gradient gives us the direction of steepest ascent of the loss function. So it tells us at this point, what direction do I need to take a step in to maximally increase this value of this loss function? And so if you know the gradient is taking you in the direction of steepest ascent, if you take a direction in the negative, you take a step in the direction of the negative gradient, you are going to take a step to try and minimize that loss function, which is our goal, right? We want to get our loss function as low as possible on our training data. That indicates that we're doing the best possible job we can of predicting the next word on this training corpus. So what are some properties of this gradient? The gradient is same dimensionality as theta. So we're going to denote the gradient using this notation dl d theta. And remember, our theta up here is the set of all of the parameters that make up the model. So what does this gradient look like? Well, it's also a set of dl dw1, dl dw2, dl c1, dl c2, and so on. So it's the partial derivative of this loss function with respect to all of the individual parameters of the network. And the gradient is just a set of all of these partial gradients together. Partial derivatives, sorry. Okay, so intuitively, what does this tell you? For each parameter, j in theta, the gradient dl d theta tells us how much L would change if you increase j, that single parameter, by a very small amount. So remember, we talked about that weight matrix W sub 1, let's say it was like a 4x3 weight matrix. So the gradient, the partial derivative of the loss with respect to that parameter is also going to be a 4x3 matrix. Each element of that matrix is telling you exactly this, how much it would change if you take a very small step in that particular value. Okay, so that is generally, at a high level, the concept of the gradient. And one of our major goals is, given the loss function and the network, compute the gradient and then use that to determine how we should update our model to minimize the loss function. So that's step 3. Given the gradient dl theta, we take a step in the direction of the negative gradient. And this is because we want to minimize our loss function, not maximize it, right? We don't want to make an even worse model than the random one that we start out with. So the goal is to minimize L. And so we can then take a look at a simple equation which defines the concept of gradient descent. So I start with a completely random set of parameters. Let's say that is called theta old, which means that this is the previous set of parameters. I don't like it. I want to adjust the parameters to make the loss go downward. So my goal is to create theta new, which is the new set of parameters for which the loss is lower. So what I do is I take my old set of parameters and I subtract some multiple of the negative gradient from this old set of parameters. So here we have this eta term. This is called the learning rate. You might have seen this if you have done any sort of model training using gradient descent or stochastic gradient descent or any other optimizer. And then we multiply the learning rate by our gradient that we compute. So what are we actually doing here? If you look at this equation, the learning rate is governing how far in the direction of the negative gradient we step. And the gradient itself is telling us what direction should we go in to minimize this loss function. And so this is a very simple equation, but it is the core of all modern language models and vision models, speech models, whatever that we see today. Any model that is trained, any basically neural network model is trained using gradient descent. And these concepts apply not only to language models, but to all of those models. So the learning rate, we can also call the step size of the model intuitively. So let's take a look just in a simple let's say we have one parameter in our network, and the loss is a function of that one parameter. We can actually plot this process in 2D and see how it works. So let's say we are going to plot on the y-axis the loss, and on the x-axis our single parameter theta here. So this is not like W1, W2, W3. This is literally just a single scalar parameter theta, that just for the sake of this demonstration. And let's say the loss curve looks something like this. So obviously our goal is to get to this magic spot down here, which is the minimum, loss minimum, right? So we want to get down here. This is the best that we can do given our current model. However, when we start, we might start at some like random point on this loss surface, right? Or this curve here. So we might start up here. Let's say this is the loss when we are at theta 0. So we have randomly initialized our parameter, and we compute the loss on our training data, and this is the loss. So now, if we compute the gradient at this point, we might, and again, let's just discuss the negative gradient here. We might get a direction that looks like this, right? So if we change our parameter in this direction, like going down here, we would expect the loss to decrease. And so we use this equation up here to take a step in the direction of the negative gradient. And then we have a new parameter, theta 1. We can recompute the loss function given theta 1, and we observe that, look, we actually managed to decrease the loss, but maybe we're not satisfied with how low the loss is at this point. Maybe we should take another step, right? So we can compute another gradient and then go down here. And so I can repeat this process until some convergence criteria is reached. And so there are many ways in which you could run this gradient descent process. You could run it for a fixed number of steps. That's what is pretty commonly done. You can also stop the process when your loss isn't improving any further. This is generally called early stopping. You might compute like how many steps have you taken without the loss improving, and if some number of steps has been reached, just terminate the training process. But there's many different ways you can do this. There needs to be some condition that is hit to stop this process of updating your parameters. So what happens if I change my learning rate, right? The step size that we talked about. So let's say like right here, I'm using pretty small step sizes. But what if I use a very big step size? So I compute this gradient here, and I take a very big step. So now I have theta 3, and I might think, oh, well, I took a huge step, so maybe I got a huge reduction in the loss. But instead, I could end up over here, and actually my loss has increased because I overshot this minimum by going too far in the direction that I had computed. And so then I might have to compute the gradient again and take a smaller step, and eventually I might get back down to something close to the minimum. Okay, so in these kinds of simple scenarios, you might be even guaranteed to find the minimum depending on the properties of your loss function. But with neural language models, the loss surface is highly non-convex, and you are not guaranteed, even if you apply this gradient descent process, to reach this global minimum of the loss surface and find the best possible model on the training data set. However, modern deep learning optimizers are pretty good. We also have better understanding of these loss surfaces. And it turns out that even if you hit a local minimum, which is what these gradient descent algorithms tend to do, that local minimum is generally very good and potentially competitive with the actual global minimum of the loss surface. So in practice, we use gradient descent even on these non-convex loss functions. That's just a detail. You don't actually need to understand any of that for this class. But I do want to talk about the optimizer a little bit, because you will see this in implementations of any sort of deep learning model. So the optimizer refers to this function up here, this gradient descent function, and specifically, how do you compute this learning rate parameter? Can you do it dynamically? Are there other approaches where you can use historical gradients from not just the previous time step, but many iterations in the past, and use some statistics to get a better sense of what the gradient is, as opposed to just using your current parameters to estimate the gradient? There's many different ways you can make this process better to guarantee or increase the chance that you get a lower loss as a result of this process. So what I've just described is called stochastic gradient descent, or SGD. A much more common optimizer is called ATOM. We're not going to get into how it works, but it generally outperforms the normal stochastic gradient descent. And there's a huge number of other optimizers. There's even a recent one called Sophia, which is specifically designed for LLM training. But in general, for most of your purposes, you can just use the ATOM optimizer in PyTorch and expect to get generally good results. Okay, so let's see if there's any questions on YouTube here. Okay, does our loss function L also need to take a parameter for some test set with which to compare our model's output to? So your loss function during this process is always computed on your training data set. The whole point is to minimize the loss on your training data, right? That's going to give you your maximum likelihood estimate. You're never going to be training on the test set. So at test time, you might want to compute the loss function, like maybe the perplexity or something on your test set, and you can do that separately, but this whole process only involves the training set, right? We never want to train our model on things that we're going to evaluate it on. All right, I will skip this research request comments. Any questions from the class? Yep. Yes. That's how, in practice, the LLM losses look. Yes. Yep. You can get stuck in local optima, and there is no good way of, you can never guarantee you will find the global minimum. However, it turns out that for all of these neural network architectures, local minima that you find are generally good enough to achieve some performance on the task. And also there's a trade-off, right? You might be able to find the global minimum that best, makes a model the best performing on the training set, but that model is not necessarily guaranteed to generalize well to a test set, right? It might have fit the training data too specifically and do worse on things that it hasn't seen before. So then there's the concept of regularizing the model. Maybe you find a model that is not as good on the training data, but is more general and performs better on the test data. So there's many different ways that, you can approach that. So the question is there a way to get out of a local minima if you're stuck there? There are a lot of approaches. One approach is just to bump up the learning rate if you haven't changed your loss that much in a couple iterations. So the idea is that maybe you'll take a big enough step that you like get out of there and go somewhere else. You can also, if you're using something like Atom, there's all of these statistics of the gradient. You can clear that, and basically the whole idea is to just take a step somewhere that you haven't been before and see if you can find something better. Other questions? Okay, so let us talk about some important hyperparameters then of this process. Of gradient descent. So hyperparameters are things that you as the designer of this model choose beforehand, and they are not learned through gradient descent themselves. So in terms of hyperparameters in this process that I've described, what are some hyperparameters that you can think of? Yeah, so the learning rate, this eta term here, is something that you might set beforehand, and maybe there's an optimizer that can dynamically update based on what you've chosen, but you still usually choose some initial learning rate to start with, and that matters a lot in terms of how your optimization process unfolds. What are some other common hyperparameters of this gradient descent process? Raise your hand. Yes. Right, so the batch size is a critical hyperparameter, and it is worth discussing more in detail. So first, what is the batch size? So this means how many training examples do you use to estimate the gradient DLD theta before taking a step. So this is a critical hyperparameter. Basically what it's saying intuitively is that if I compute the gradient using a lot of different prefixes, so students open there, the cat walked to the blank, you know, class starts at 2:30 blank, I mean, all of these different prefixes, and I compute the model's prediction of the next word, I compute the loss function on top of that, I average or sum all of these prefix-specific losses together. The idea is that if I use a bigger batch, so more examples with which to compute this loss function, I'm going to get a better estimate of the gradient of that specific parameter configuration, right? So if I just say students open there, and my model gives me some distribution, I compute my loss function only on this one example, I don't really know how the model performs on, say, you know, I walked my blank, right? I don't know if the model is good or bad on that. And so I am changing my model's parameters specifically on just its performance on this one prefix. So intuitively, if I have more examples of how good or bad the model performs, I'm going to have a better idea of how to estimate it, estimate the gradient, so that when I take a step, I'm going in a more productive direction overall. That's the idea. However, there's a trade-off between, so it might be always good to have a higher batch size, larger batch size, because you get a better estimate of the gradient. But it's also more expensive to compute the gradient or do this process if you have a bigger batch size, because you are taking fewer steps if you're using more examples to estimate the gradient, right? So let's say I have 1,000 examples in my data set, and I set the batch size to 100. This means that I will be able to take 10 steps before I take a full pass through my training data set, right? Versus if I, say, use a batch size of 1, I will now update my model 1,000 times before I start looking at the training data set again. And so there are trade-offs between both of these. It's generally more expensive with a larger batch size. You might see convergence faster with a smaller batch size. But if you have the compute for it, people generally recommend using a larger batch size to kind of max out your GPU memory. So in practice, the way people set the batch size is usually to maximize their GPU's utilization. So it's basically like a hardware dictated constraint rather than trying to use a smaller one or a larger one based on performance. Okay, and your homework 0 gives you some more practical, hands-on, applications to doing some mathematical operations with a batch of examples. All right, so that is gradient descent at a high level. Now let's start specifying the first 2 steps here. So the first step was to define a loss function, but I didn't tell you what that actually means, right? What is the equation that we're using here, and why are we using this particular function? So let's start there. Okay, so our loss function is the cross entropy loss. And so the way it works is quite simple. You can just think of it as the negative log probability of the correct next word in the training data given the prefix. But we'll actually go through why this makes sense for the task and why are we even calling this thing cross entropy loss. Okay, so let's say we have our prefix here, students open there. And so this is our training prefix, one of many prefixes in our training data set. We know that in our training data set, books is the word that we actually observe after this prefix. That's what was given to us in training. We had some sort of document that mentioned students open their books. Okay, so this we're going to call our target. And if you think about language modeling as a classification problem, right, our softmax layer produces a vector of size v, right? So there's v possible labels. So essentially the size of the output space is v, the size of the vocabulary, and we are trying to maximize the probability of books and minimize the probability of all of the other words in the vocabulary given this prefix. That is our maximum likelihood estimator here. So let's take a look at our high-level goal, which is maximize P of books given students opened there. And this is equivalent to minimizing the log probability of books given this prefix. So our loss function that we use in language modeling is literally just the negative log probability of the ground truth next word. So our loss is negative log of P of books given the prefix. And so this intuitively makes sense, right? This is what we want. We want to maximize the probability of books given the prefix, but our gradient descent formulation requires the loss function to tell us how bad the model is doing. So we're going to use the negative log probability as the loss function, and we're going to try and compute the minimum of this. Okay. So again, this is the negative log prob of the correct next token. So intuitively, this makes a lot of sense. This is exactly what we want to optimize. But why do we call it the cross entropy loss, right? This seems like it's just focusing on a single word and doesn't have anything to do with the distribution over all of the words, right? So this also applies to our concept of the maximum likelihood estimate. So Y cross entropy loss. And let's take a look at two different distributions here. We have the model's predicted distribution. So let's say that we have our model, I'll just write it out here, NLM of students opened there. So this means I'm putting this prefix into my, say, concatenation-based language model. And what is the output of this model? Well, it's a distribution over the words in the vocabulary, right? So in our example from before, I had like these words, stamps, books, lamps, or something like this, and I had some probability on each of these words. And so this right here, let's call the model's predicted distribution. So we will call it Q, the model's predicted, wow, that was really bad. Model's predicted distribution. So this is one thing that we get out of our model, but the other thing is the distribution that we observe in our training data. So in our training data, we actually have all of the probability mass concentrated on the ground truth next word. So we had stamps, books, and lamps. We have 100% of the probability going to books, because this is what we observed in our training data set. We did not observe ever students open their lamps. This has a 0% probability. So what our loss function is doing, maybe I'll color this differently, is it is trying to make the model's predicted distribution, this Q over here, as similar to this training data distribution as possible. And you can see intuitively that the training data distribution only puts probability on one word, which is the correct next word, right? So this is what the model is actually trying to optimize. And if you are familiar with the definition of cross entropy, it's basically a kind of distance measure between two different distributions. And so we can compute this by summing over all of the words in the vocabulary, this product of the training data distribution times the log of the model's predicted distribution. So this is the definition of cross entropy that many of you have probably seen before. And so if you look at this equation here, you'll see that this is the this is the training data distribution. This is the model's predicted distribution. And this term here is 1 when W equals books and 0 otherwise, right? Based on the the training data distribution putting 100% of the probability mass on the word that is observed in that training data. So you can see that this equation then just simplifies, right? We don't need any of this summation anymore. It simplifies to negative log Q of books given students opened there. So you can see that if you wanted to use, optimize something differently, so maybe you wanted to, instead of training your model to put 100% of the probability mass on books, you wanted to instead say, well, maybe I can apply some smoothing so that it's not so confident in books and it puts some non-zero probability on every other word. We learned this concept of smoothing before in n-gram models, right? I can apply the same thing here, where I might be able to put like some non-zero probability here and decrease this probability to say 95% or something. And now I have a new training data distribution, and I can no longer simplify this cross-entropy loss to just the negative log probability of the correct word, right? I actually have to take into account all of the words in the vocabulary because they are not all 0 anymore. And so that technique that I just described is called label smoothing, and it is a fairly popular technique for training language models, but we will not cover it anymore in this class, so I will just delete that from the figure to avoid confusion. Okay, so any questions on the loss function that we're using? Let me check on YouTube. How do we construct the network to get embeddings with respect to LMs? Like in CNNs, we use filters to construct these features for images. There's nothing special about obtaining the embeddings. They are the input layer of the model. So you randomly initialize a matrix, you randomly initialize all of these vectors, vector embeddings, and associate one of these embeddings with a particular word type. And then your network just uses those embeddings during training. So there's nothing special like filters or anything like that. Does it happen that all of the individual gradients may not reach local minima, may not reach, okay, so like maybe you optimize weight 1, but weight 2 isn't. I don't really know what that means because you're adjusting all of them at the same time. So, you know, your update for weight matrix 1 might be at a local minima if you froze every other parameter in the network, but it depends on the values of the other parameters. So I'm not sure how to answer that. When is label smoothing commonly used in NLP? It is definitely used in machine translation, at least a couple years ago. It is used in the original transformer paper. So yeah, I'm not really sure whether it's like a default in any of the PyTorch loss functions, but I think it is still used. I'm not sure exactly where these days, or if it is even used in modern LLMs. That's a good question. So if I remember to look it up, I will post it on Piazza later. All right, so let us move to the last part of this class then for the last half an hour. So we've covered step 1 in detail. We now know how to compute the loss function given a set of parameters and given a training data set. We just compute this cross-entropy loss. Now we have to figure out how to compute the gradient, right? So that was a critical term in gradient descent, but I didn't explain how you actually get it. So maybe I'll just start on the new page. The algorithm that we use to compute the gradient in neural networks is called backpropagation. To compute LB theta. And it allows us to compute it in an efficient manner, as we will see. So a critical property of backpropagation is that it relies on the chain rule of calculus. And so you can compute the gradient just naively using the chain rule. But as we'll see, backpropagation is just a tweak on that, which allows you to cache some of the terms that you use to compute the gradient, the partial derivative with respect to one parameter, and reuse them when you're computing the partial derivative of another parameter. But it's very straightforward. You know, if you haven't touched your calculus in a while, these are all fairly straightforward. We're just taking derivatives of simple functions. You should know the intuition, and you should be able to at least take some simple derivatives for example, the exam. So if you don't really understand what we're doing in this part of the class, try and study on your own and figure out to the point where you're able to follow along with every one of the steps. Okay, so to illustrate this process, we are going to use a very simple neural network. There's going to be no weight matrices and no vectors. We're just going to use single scalar numbers for every step of the network. So we're going to start with some input here. We'll call it x. And we're going to have a hidden state, which again is a single scalar. And we're going to have an output. So to go from h to x, we're going to use this weight parameter w1. And to go from h to o, we're going to use another weight parameter w2. Again, these are not matrices for this example. They are just numbers. They're just individual numbers. Okay, so our input, when we are doing training, we have access to input-output pairs. So x is an input, and y is a target output. This is like the thing that we are trying to predict. So in this case, x and y are both numbers. So maybe I expect when I input the number 1.5, my output is going to be 2.4 or something. We just have some random mapping for the sake of this example. So it could be, for example, like, I don't know, 1.5 and 3.4 or something. Okay, and O here is the, oh, I should not use an arrow just to avoid confusion. See, O is the model's prediction. So we're going to compute a loss, which is a function of O and Y, right? Y is the target that we want to predict. O is what the model produced. My loss function is going to tell me how wrong is O, right? If you know that the right answer is Y. All right, so let's write some equations now. We're, again, using a very simple network. We're going to set our nonlinearity to the tan h function, which is a common one for these kinds of simple networks. So to get h, we're just going to take this nonlinearity and apply it to w1 times x, the product of two scalars. And then for O, we're just going to take our nonlinearity and apply it to W2 times H. So again, in the feed-forward network that we looked at, O was actually softmax of a matrix times a vector. Here we're saying O is the tan H of two numbers multiplied together. Just for simplicity, the concepts apply no matter what F is set to and whether W is a vector or a matrix or a scalar, this algorithm applies just the same. All right, so let's follow our steps now. The first step is to compute the loss function L. So what are the parameters of this network? Let's assume that x is given to us. We're not learning x. What are the parameters of this network? Right, there's only two parameters, right? We have W1 and W2. So this makes up our theta. And then what do we actually want to compute? The gradient is just dl dw1 and dl dw2. So if we're able to compute both of these partial derivatives, then we are able to compute the gradient, right? So this is our goal here. And this is what we want to end up with when we get through this process. So the loss function that I've just explained to you, the cross entropy loss, is unnecessary for such a simple task like this, where you're just trying to map numbers to each other. So we're going to use the most basic loss function there is, which is the square loss. So this is 1/2 times y minus O squared. So if you think about this loss function, it basically is high when O is very different from y, and low when y is similar to O. It's always positive, right? It's a square. So this is called the square loss, or the L2 loss. It's very commonly used for regression problems. We're not really going to talk about regression problems. However, it is quite useful for if you want your output to be a continuous value like 1.6 instead of discrete output like a word or something like that. You generally use a loss function like this. So again, our y here is the target, our O is the model's prediction, and you can clearly see that this L tells you how bad the model is on this specific example, right? Okay, so let's get started with computing the gradient. So we want to compute dl dw1 and dl dw2. And so the key thing that we're going to use here is the chain rule of calculus. So just as a refresher, and remember, we already covered the chain rule of probability. Both of the chain rules are completely essential for neural language models. If we want to differentiate the function g of f of x, we are going to first differentiate g with respect to f and take the product with the derivative of f with respect to x, right? This is very basic thing that you probably learned in like the first or second lecture of calculus. And that's all the math that we really need to know in order to compute this, these derivatives. So let's start by computing dl dw2 here. So if you look at our loss function, we're going to start with our loss function here. So this is our current goal. L equals 1/2 of y minus O squared. So I don't actually see a W2 in this loss function, right? However, I know that O is a function of W2, right? The output of the model, we use W2 to get it somehow. So let's take a look at our equations again. We see that O equals tan h of W2 times h. So we know that O equals tan h of W2 times h. And so we kind of need to work our way backwards. From the loss, we see that O is used, and then work our way back to W2 using the chain rule to get this product. So I'm going to define some intermediate variables to make this easy to visualize. Just two intermediate variables. So I'm going to say that variable A is W2H, so this is the thing in the tan H, and B equals W1 times X, which is the thing that is inside the tan H for X, for H. And there's also one derivative that you need to know in order to do this process. So if you want to differentiate tan h of x, its derivative is 1 minus tan h squared of x. So this property of the tan h function makes it very attractive for gradient descent. If you can see this, the derivative of tan h x, you've already computed tan h x during forward prop. So if you want to compute the derivative, you just square it and then subtract that squared term from 1. So the computation is pretty less when you have this activation function. All right, so if I assume all of these things here, so these are my intermediate variables, this is the derivative that you need to know. And if you have to do backprop on the exam and we give you some function like this, we will also give you its derivative, so you don't need to like memorize this or anything like that. All right, so let's rewrite our equations now to include these intermediate variables. So specifically, I have O equals tan h of A, and then I have A equals W2H. So if I want to compute dl dw2, I'm going to use the chain rule to expand this out into the product of these partial derivatives. First, I'm going to compute dl do, so that gets me from here to here. Then I'm going to compute do dA, which gets me from here to here. And finally, I'm going to compute dA dw2. And in isolation, each of these partial derivatives is very easy to compute, right? So let's start with this one. If you look at dl and then you look at dl do, the partial derivative is quite straightforward. So if you remember from basic calculus, I have this squared term here. I'm going to multiply it with the rest of the equation. So I get y minus o. And then the o also has a negative attached to it, right? So my entire partial derivative here is just going to be negative y minus o, right? This is just basic differentiation. So now let's look at do dA. Here we have o equals tan h of a, so we can just use this derivative that I've provided you before, right? So 1 minus tan h squared of a means that this is just 1 minus o squared. So I can use the value of o I computed during forward propagation and simply just apply this formula to get the partial derivative that I need. And finally, dA dw2. This is probably the most straightforward one, right? It is just w2 times h. So this partial derivative is just h, right? And so now you can see through the application of the chain rule, I have computed one of these terms in my gradient. And now all I have to do is compute the other term in the gradient. So let's just take a look at how that works without writing down explicitly the terms. So actually, let me move this a little bit. So let's just copy some of these things again. We have L equals 1/2 y minus o squared. O equals tan h of A equals W2H. And now we have a new equation, right? H equals tan h of B. B equals W1X. And so this is like the very first layer of our network, right? The input, the very first thing that's happening is we multiply W1 by the input X. So now, given all of this, let's work our way backwards to get an equation for dl dw1. We start with dl do. So remember, our goal is to get all the way from this L over here to this W1 down here, right? And so we're just going to work our way backward. We see that O equals tan h of A, so we're going to do do dA, dA dH this time. So remember, we're not stopping at W2. We want to actually get the partial derivative with respect to W sub 1. So we are going to go down here and into the H, dH dB, and then finally dB dW1. So this expansion gives us the partial derivative that we want. And so if you look at dl dw2 and dl dw1, you actually notice that they share two terms, right? So in particular, this term and this term are identical for both of these expansions. And so if I'm going to compute dl dw2 first, which is what I should do because it's higher up in the network, I've already computed these terms, so there's no need for me to compute them again when I'm computing dl dw sub 1, right? So the algorithm of backpropagation works essentially by using the chain rule, but also caching the partial derivatives that you've computed at higher levels of the network and reusing them when you go down further to compute the partial derivatives for parameters that are used at the bottom of the network. Does that make sense? So let's just write that down. Backpropagation chain rule of calculus and caching previously computed derivatives. So note that I'm not caching all of these derivatives, right? Like this one, dA dW sub 2, is not useful anymore because it leads to the specific partial derivative with respect to W sub 2. So it can never be useful when I'm computing the derivative of another parameter lower down in the network. Okay, so then the final step, like we've computed these partial derivatives, what do? Step 3, update the parameters. And in this example, we only have 2 parameters, so we have 2 equations. W sub 1 new equals W1 old minus eta times dL dW1, and similarly W2 new is W2 old minus eta dL dW sub 2. So I computed my loss function, computed the gradient, and then used it to update both of these parameters. And the idea is that my new loss function is going to be lower than the one that I had for these old set of parameters. All right, does that make sense? Any questions about backpropagation? Okay, so one thing to note is that this is a very simple example, right? I have just scalars in this example. But when we're talking about neural language models, we're always using matrices and vector embeddings, right? And when we use batched stuff, sometimes we even have to consider 3-dimensional tensors if we have like a sequence of embeddings. So things can get much more complicated than just this example. However, if you are implementing a neural network in, say, PyTorch or TensorFlow or one of these libraries, you might be thinking that, oh my God, I have to compute all of these derivatives and write them out. But those libraries, their whole purpose is to automatically compute these derivatives for you. So for example, in PyTorch, you just have to define the forward propagation method for your neural network. So like, what is the structure of the network? How do you get from the input to the output? Like, do you have a linear layer? Where do you have your softmax layer? All the easy stuff, right? And then if you compute a loss in PyTorch, so let's say in PyTorch I have a model. This is my neural language model. I use my model to compute the next word prediction, the distribution of students opened there. Then it spits out some distribution. Then I can compute some loss term using this distribution. So maybe let's call this O. The loss is the negative log probability of, so let's say books. Okay, I'm not going to write it out like this, but the loss is essentially a function of O and the ground truth word that occurred next, which is books, right? So what does the model actually put, what probability does it put on books? So actually, let me just write it out correctly here. E loss equals model of books given students open there. And I'm sorry, negative log probability of this whole thing. All right, so this is how we defined our loss function. And so now I'm going to just compute the cross entropy loss like I've described here. And in PyTorch, to compute the gradient, I just call this loss.backwards function. And that will just compute the gradient for you using the backpropagation algorithm. you don't have to worry about the chain rule or caching or anything like that. Everything is done for you, and then you can use it to update your model by, yeah, essentially using whatever optimizer that you want to use. So when you have some more hands-on experience with these models, likely in your final project, you will encounter this kind of thing when you're building your models. So just know that you have just understood the intuition and a basic example of backpropagation, but what goes on under the hood is much more complex in terms of the computations for very complex functions and so on. I will share a video on the course webpage of deriving the gradient through a linear layer. So you have a matrix and a vector, and you want to compute the derivative through that. So you can get a sense of what kinds of computations are actually happening with a library like PyTorch. But overall, like, the general concept is the same, and we're still using all of the chain rule and caching that we've seen before. Okay, let me check on YouTube if there's any questions. I have rarely seen this before, so okay. So I guess anyone here have questions? All right, so I will see you all on Monday when we're going to start talking next week about transformer models and yeah, more modern stuff.